and the topic of today's video is going to be limiting reactant. So what we're trying to determine in a limiting reactant problem is which reactant do we run out of first, and why is that important? Well, the importance of it is because that is going to in turn dictate the amount of product that we can in turn form. All right? So let's take a look at the simple reaction that we've already dealt with. So here's a balanced reaction equation. We can burn magnesium in the presence of oxygen to make solid magnesium oxide. Here's the balanced equation as we looked at it in class. Now normally we wouldn't need to worry about this because we'd be doing this in the open air, so we'd have some fixed amount of magnesium, but because there's an unlimited supply of oxygen in the air, we would just say that oxygen is by default the excess reactant. In other words, we can't run out of it because we have an unlimited quantity of it in the air. By default then, the magnesium would be the limiting reactant. So in that sense, the amount of magnesium oxide that I can make is going to be based upon which reactant I run out of first, which in this case is going to be the magnesium if I had an unlimited supply of oxygen. But let's say we're going to set the problem up in a little bit different way. Let's say that we're going to do this reaction in a closed vessel such that I'm starting out with 10 grams of magnesium and 10 grams of oxygen. So I have a fixed amount of each reactant that I'm starting with. So now it's not obvious to us which reactant we're going to run out of first. So we have to do some math to determine that. All right? So here's one way to set up a limiting reactant problem so that I can determine which reactant I'm going to run out of. All right, so it might look like I've got the same amounts of each reactant. In terms of mass, that would be correct. But we also know that when we make distinctions between different things in balanced chemical reactions equations, we know that we use the mole. All right, we never use grams directly, so we have to make those conversions, those comparisons in the mole. All right, so what I'm going to do is I'm going to pick randomly one of the reactants. So let's just pick oxygen. For no good reason, I'm just picking. All right, so the first thing I'm going to do is I'm going to take my 10 grams of oxygen and I'm going to use the molar mass of oxygen to get to the moles of oxygen that I've got available. Okay, so grams of oxygen will cancel with grams of oxygen, and I know that I have 0.3125 moles of oxygen, to correct sig figs here, available to me. So here's the question. I want to now find out how many moles of oxygen I need to fully react with all of the magnesium that I have. So to do this, I can use my mole bridge. So I can relate moles of magnesium and moles of oxygen through that mole bridge. All right, so now I'm going to start from the standpoint of magnesium and then use my mole bridge to determine how many moles of oxygen would be needed to use up or react with all of the magnesium available. All right, so I'm going to start with my 10 grams of magnesium. I'm going to convert it to moles so we can make the comparison. So grams of magnesium will cancel with grams of magnesium. All right, I now know that in my balanced equation, for every 2 moles of magnesium, I need to react with it 1 mole of oxygen, hence the 1 to 2 mole ratio that we see here. That comes directly from our mole bridge. So moles of magnesium will cancel with moles of magnesium. I'm left with moles of oxygen. And to my 3 sig figs, that's 0.205. This would be the number of moles of oxygen that I need to use up all of the magnesium. So now what I need to do is, since I've got both of these now in terms of oxygen, I make a direct comparison between what I have and what I need. All right? So I have available to me 0.3125 moles of oxygen. To use up all of the magnesium, I need to use up 0.2057 moles of oxygen. So what I see here is that I have available to me more oxygen than I need. So as a result of that comparison, what we now know is that oxygen is what we call the excess reactant. I have more of it than I need. So it's going to be an excess at the end of the reaction. Also, by definition, that makes magnesium the limiting reactant. Since I have less of it, that means that I'm going to end up using it all up. All right? So magnesium becomes the limiting reactant. So at the end of the reaction, I have no magnesium left. and I still have some excess oxygen left over because I had more than I needed in order to satisfy the stoichiometry of the equation. So now I can go about calculating what I call the theoretical yield of magnesium oxide. So that's the amount of product in this case that I could actually make using my limiting reactant. Now again, remember, the limiting reactant dictates the amount of product that I can form. So if I say that my magnesium is my limiting reactant, then I need a mole bridge that takes me from magnesium to magnesium oxide in order to determine the mass of the magnesium oxide I could theoretically make. All right? So let's go ahead and do that calculation. Since magnesium is my limiting reactant, I'm going to start with it. So I've got my 10 grams of magnesium. I'm going to convert it to moles. I'm then going to use my mole bridge to go between magnesium and magnesium oxide. Balanced chemical reaction equation tells me that for every 2 magnesiums I use up, I'm going to make 2 moles of magnesium oxide. So there's my ratio of 2 to 2 of each mole. So my moles of magnesium cancel top and bottom. I'm left with moles of magnesium oxide. Now all I need to do is convert that to a mass using a molar mass of magnesium oxide. So every mole of magnesium oxide will cancel with moles here. I got 40.304 grams of magnesium oxide per 1 mole of it. And when I work through the math here, I find that from a theoretical standpoint, from the limiting reaction standpoint, I should be able to make 16.6 grams of magnesium oxide. So now, the last thing I want to show you is just a second alternative way to calculate limiting reactant. All right, for you guys who might want an alternative method for determining limiting reactant, another way in which we can do this is to take your masses of both reactants and converting those over to either moles or grams of product. So ultimately, the one that gives you the less amount of product, either in terms of moles or grams, has to, by definition, be the limiting reactant. So let's go ahead and make that comparison using this alternative method. So I'm going to start out with my magnesium. I got my 10 grams of magnesium. I'm going to convert that to moles of magnesium, and then using my mole bridge over here, right? For every 2 moles of magnesium that I use, I'm going to make 2 moles of magnesium oxide. I've got my mole ratio now of 2 to 2, so the moles of magnesium will cancel. I'm left with moles of magnesium oxide, and I get 0.4114, and it's 0.411 to sig figs here, moles of magnesium oxide. Now again, I can take that to grams if I want to, in order to get a theoretical yield in terms of mass. Now let's go ahead and do the same calculation for oxygen and see what we get. Starting out with my 10 grams of oxygen, I'm going to convert that to moles. So grams of oxygen cancel. I'm going to use my mole bridge. I know that for every 1 mole of O2, I'm going to make 2 moles of magnesium oxide over here. Hence my ratio of 2 moles of MgO to 1 moles of O2. Moles of O2 cancel top and bottom. And when I work this out, I get 0.625 moles of magnesium oxide. And when you do this, you're going to notice that the oxygen gives you more moles of magnesium oxide. Okay, so that's a larger quantity. So what that tells me then is that the magnesium, since it gives me fewer moles of product, has to be my limiting reactant. And that means also that my oxygen has to be my excess reactant. All right? So now if I wanted to take this all the way to the theoretical yield, it's easy to do. All I have to do is, from the standpoint of my limiting reactant, put one more conversion on here, where I'm going to convert moles of MgO to grams of MgO. So I know that for every 1 mole of magnesium oxide, I think I had 40.304 grams of magnesium oxide. All right? So moles will cancel top and bottom. And when I work this out, I ought to get the same theoretical yield that I got before, which I think turned out to be, what, 16.9 grams of magnesium oxide. All right, so that's an alternative way to get to the theoretical yield and also determine what the limiting reactant happens to be. So we're going to practice more with this in class on Friday, and we're also going to see how to calculate an excess amount of a reactant. So we'll see you then.